Thank you for taking time to do this interview with me today. And I just want to give like a brief context. My name is Annie, and I created the website Sustainability Beyond the Lab um, to showcase modern sustainability research as well as the barriers that prevent it from becoming widely adopted. And I just want to jump straight into your work. Could you give kind of
Mhm.
like a brief introduction of yourself as well as your work in the Long Lab, the Brushett Lab, as well as in industry?
Yeah, my name's Arun Johnson. I'm a third year, going to fourth year PhD student in the chemical engineering department at MIT currently. Previously, I worked at a startup called Terraform Industries in Los Angeles, and before that, I was at the Long Lab at Berkeley. Um, my research now, actually, I guess we can start going
Yeah.
chronologically. Back when I was at Berkeley, I was working on a class of materials called porous aromatic frameworks. And specifically, we were trying to make new versions of these materials that we could use for water purification. So that could be either trying to remove toxic ions from water, things like chromium and arsenic that are toxins that can just be found naturally in groundwater in some parts of the world, as well as extracting valuable resources from water. So you can imagine, for example, that there's a very small amount of gold or silver that's dissolved in water, or
Mhm.
maybe a larger amount dissolved in waste from uh, mining facilities or from places where you're reprocessing electronics waste.
Yeah.
And if you could extract that out of the water, you would both help detoxify the water and also recover valuable resources in a way that might be less energy intensive than if you were to mine them out of the ground fresh. So that was the work that I did in the Long Lab. And then I went to work at Terraform Industries for some time. There we were developing something called uh, synthetic fuels. So the
Mhm.
idea is we would have three separate machines, one which would produce hydrogen out of water, another which would capture carbon dioxide from the air, and then a third which would combine the hydrogen and the CO2 together to make fuels. And you could use that to make, for example, natural gas or fuel for planes or for international shipping, a variety of different products. And the idea is that you're still making hydrocarbon fuels that all of these, all of this existing infrastructure is already used to running on. So you don't have to change anything about the planes or the boats or anything that
Yeah.
you're running with this. But now, since you're making it out of CO2 that you captured from the air, it's carbon neutral. Rather than taking new carbon out of the ground, burning
Mhm.
it, and adding more CO2 to the atmosphere, we're just recycling it. And synthetic fuels are an interesting idea, but the problem is that they're very expensive to make at the
Mhm.
moment. And so it's not really competitive on an economic basis with just mining fossil fuels and
Yeah.
using them directly. And most of the cost of synthetic fuels, both in terms of the energy required to make them and in terms of the dollars required to make them, is ultimately from the hydrogen that you need to make them. So again, there was the two components, the CO2 and the hydrogen. The
Mhm.
hydrogen is the more energy intensive and the more expensive part to
Mhm.
produce. And so I, after I left Terraform, I came to MIT to work on new types of devices for producing hydrogen, with the hope of making cheaper green hydrogen. And that's what I work on now.
That's really interesting, your work in both like academia as well as industry, creating like hydrogen fuel as well as these natural gases by combining it with carbon dioxide. If I can ask, like, what is kind of the problem that um, your research kind of aims to solve, as well as how does it bridge a solution?
Yeah, so with hydrogen, it's already a very widely used chemical around the world for a few different purposes. It's used to make fertilizer, it's used in the petrochemical industry, it's
Mhm.
used to make chemicals for the chemical industry, for other industrial manufacturing processes, and increasingly it's starting to be used to produce steel as well. But almost all of the hydrogen that's produced today comes from a method called steam methane reforming,
Mhm.
or from another related method called coal gasification. Both of those methods are very carbon intensive. You produce the hydrogen by taking fossil fuels, either coal or natural gas, and reacting them at high temperature with steam. And that produces hydrogen, but for every kilogram of hydrogen you get out, you get 10 to 22 kilograms of CO2 in a typical
Mhm.
process. And so, because of that, we use about 100 megatons per year of hydrogen, and producing that much is responsible for about 2% of global CO2 emissions just for producing hydrogen. So, for a long time, there's been interest in trying to produce hydrogen instead through a green method that doesn't involve producing CO2. And the most prominent option there is to produce it from water. So you can
Mhm.
split water apart using electricity into hydrogen and oxygen. And then there's no carbon involved in the process.
Yeah.
But
Oh, continue. Yeah.
yeah, there's two major factors that drive the cost of producing hydrogen from
Mhm.
water splitting. One is the cost of the electricity you need to power the process, and the other is the cost to actually build the devices that are going to use the electricity to split the water.
Mhm.
Historically, the cost of the renewable energy has been really the dominant factor here. But as renewable energy has got cheaper and cheaper, now the cost of the devices themselves is becoming significant as well.
Mhm. Yeah, that's really interesting, like the cost aspect of that. Is there anything that is particularly like new or unique with the work that you're doing on hydrogen production, especially like those reactor systems?
Yeah, so we're working on a new type of device for splitting water, and the hope is that this type of device would be somewhat cheaper than existing methods.
Mm.
So there's several types of devices that you can use for water splitting. Some of the common ones that are used industrially are the alkaline water electrolyzer, the proton exchange membrane electrolyzer, and the solid oxide electrolyzer. And each of these three different methods, each of these three different architectures come with different trade-offs. Some are more efficient, but then they're more expensive. Some use precious metals, some of them don't. Some of them have longer lifetimes, some of them have shorter lifetimes. And so, depending on various factors, how expensive your electricity is versus how much you care about the cost of the device, you might prefer one method over another. But all of these architectures are fairly expensive in terms of the cost of the device compared
Mhm.
to what we'd want to get hydrogen really cheap enough to compete with
Yeah.
fossil fuels. And so we're trying to work on a totally new type of device that would hopefully occupy a new part of this trade-off space where it would be even cheaper than any of these other methods.
Mhm. Yeah. I think definitely it's interesting to hear how the cost of hydrogen production is kind of what limits its scalability as well. Um, and yeah, but would you say any other like factors besides cost, maybe policy or even the scientific innovation itself, prevent the wide scale adoption?
Yeah, with policy, it's a bit difficult to think about whether it's sort of stopping adoption versus just not facilitating adoption.
Hmm.
The default, if there was no policy intervention, is that we aren't going to have green technologies develop as rapidly because we've already put so much work historically into developing the existing fossil fuel-based economy that we have.
Hmm.
Um, Certainly, if there was more subsidization of new green technologies, that would help accelerate their development.
Yeah.
And really, what you're hoping for with subsidization is that you can put enough money in initially into research and development and scaling up commercial deployment of these technologies that they become cheaper than the existing technologies, and then you don't have to subsidize them anymore. They just compete on their own in the world economy. And
Yeah.
that's what you've seen with things like solar panels that have been massively successful. They required a lot of subsidization to
Hmm.
get them going in the first place because early on they were hundreds of times more expensive as a way to produce energy than, say, just burning fossil fuels in a natural gas turbine. But now they're often cheaper than constructing new gas turbines.
Then kind of moving on into like future sustainable research, in maybe 10 or 20 years, what would you say is kind of the most promising or has the most potential sustainable technology in your field or maybe even in general?
Um, I mean, I think as we alluded to a little bit earlier, solar panels have already been massively successful.
Hmm.
Wind is also getting much cheaper over time. These have been some early success stories in the fight against climate change. Um, Often what you're seeing is that what's limiting the deployment of solar and wind now is not so much the economics of building these methods of power generation, but rather difficulties with deploying them at a wide enough scale by integrating them into the grid, making sure that they are able to supply power that we can use throughout the entire day or throughout multiple seasons when you have variation in how much is being produced. And so there, the technology everyone is really excited about is advances in batteries, because if we have better battery technology, then we can make better use of solar and wind that are already very advanced technologies.
Yeah.
And so I think there's a very wide expectation and a lot of data to back up the idea that we're going to see massive deployment of these sort of grid scale batteries in the next 1 or 2 decades. We're already seeing it now, but it'll expand
Yeah.
substantially.
And then last question, is there anything during the interview that we didn't get to touch on or you think is particularly important for general audiences to know?
Yeah, I mean, there's certainly more we could talk about in the policy space. I know I sort of went back to talking about the economics
Yeah.
from the policy. Um, a lot of what technologies end up getting used is down to economics, and policy sort of is a lever that we can use to tune
Hmm.
the economics or help make things more viable when they're not initially economically viable on their own. But there's many ways that you could implement that. So, for example, through carbon taxes, that's one very widely discussed method
Hmm.
that could be used to just generally incentivize development of new green technologies without favoring any one particular technology over another one. We also briefly talked about the issue of, the size of relative markets that could interact with carbon dioxide. And I think that's one reason to think that we might need to sequester carbon dioxide in the long term. That is, rather than capturing it and
Yeah.
turning it into valuable products that could be sold, capture it and find a durable long-term method for
Hmm.
storing it.
Yeah, thank you so much for taking time out of your day to do this interview with me. It was really interesting hearing your research and how innovative it is, actually, as well as your perspective on scaling up these technologies.
No problem. Thanks for taking the time to talk.